you guys have your notes from yesterday, we started looking at different types of sequences. We started looking at arithmetic sequences. Today we're going to look a little bit more at geometric sequences. Again, yesterday, arithmetic sequences where we add or subtract to get to the next number. Geometric sequences are when we're going to multiply by the same number. They'll also say there's a constant proportional change. So instead of saying there's a constant rate of change, this has a constant proportional change. Again, it's going to look like we're multiplying by r, where we call r our common ratio. So kind of like how we called our common difference d. For geometric sequences, we're going to call our common ratio r. And again, they put r into two different places into these two formulas. There's two different formulas you can use depending on what they give you. If they give you, again, both of these are always going to give you g of n. So if you want g of n, you can use either one. If they give you g of o specifically, where g of o is your initial value, where are you starting typically when you plug in a 0? So sometimes they might give you that. If that's true, you're just going to take r and raise it to the power of n. They could give you a value of g at a specific k value. Again, that would be like my kth term, depending on what k is. And then again, r is my common ratio. So. Did this not turn on? I thought I did turn it on. Is it turned on? Is it broken? You should notice when we start graphing these. Oh, sorry. I was going to bring it and then I forgot. I was going to call her and then I forgot that too. There you go. Thank you. So geometric sequences are going to behave like exponential functions, except again, we're not going to connect them. So we'll kind of see what that kind of looks like when we do this one over here. Again, geometric sequences, you should notice, are going to always increase by a larger amount each time. It's always going to be by a percent. It's always the same percent each time that we're multiplying by. So for an example, here they give us a geometric sequence. They give us g of n is equal to 8 times 1/2 to the power of n. They found to find g of 0. Plug in a 0. What's anything to the power of 0? 1. So I get 8 times 1 gets me 8. G of 1, and you can kind of go to 0. I can plot an 8 on my graph if you want to put an 8. If I want to find g of 1, again, I want to take this. I'm going to plug in a 1 to the exponent. That gets me 1/2. Again, that's like half of 8 would get me 4. At 1, I can go to 4. At 2, I'm going to do 1/2 squared. If I do 1/2 squared, I get 1/4, which is like 8 over 4, which simplifies to 2. And just to do one more to check, if I do 1/2 to the power of 3, should get 1/8. 2 times 2 times 2 gets me 8. I get 8 over 8 gets me 1. So you can kind of see if I do one more. What's my pattern? Can you guys see the pattern? You could say dividing by 2. I'd rather say what we're multiplying by. So dividing by 2 is the same thing as multiplying by a half. It is dividing by 2. You could kind of say dividing by 2. I'd rather kind of, when I'm mostly talking about this, talk about what we're multiplying by, because that's going to be r. So Here we're multiplying by a half. So again, g of 4 would be a half. And you can kind of tell if I wanted to keep graphing these, I kind of stopped at 2. This would go to 2. 3, this would go to 1. 4, it's like a half. 5, it gets even smaller, and it'll get even smaller and smaller and smaller as I get to, it's going to keep getting to be a smaller fraction. I'll get 1/4, 1/8, 1/16. So my graph would look kind of like that. Now again, if I connected this, if you remember anything from Algebra 2 last year, that's an exponential graph. It looks kind of like a curve like that gets really small, close to 0. But again, for geometric sequences, we don't have to connect them yet. But it follows a kind of an exponential curve if you look at the graph, should. Again, they could ask if it's geometric or not, and they could give you kind of a formula. So again, they might want you to start plugging stuff in. If I plug in a 0, 3 times 0 is just 0. Careful. Here I'm plugging in a 1. 1 times 1 gets me 1. 3 times 1 is 3. If I plug in a 2, I get 2 times 2 is 4. 4 times 3 is 12. You should notice right away that's not going to work, right? And if you want to do one more just to check, I get 9 times 3. 9 times 3 is 27. I can't multiply to go from 0 to 3 because anything times 0 wouldn't work anyway. This is times 4. This is times some other weird number. So it'd be a fraction to get to that. So again, because it's different multiplyings, I know that's not geometric. Wouldn't be arithmetic either. That one would be neither. Typically, if you notice that n is up here as an exponent, that typically is going to mean it's geometric because you look at kind of these two formulas, right, for my geometric, the n's kind of an exponent. So I'm guessing this one probably is going to be geometric, but just to check, we should plug stuff in. So if we plug in a 0, we get 0 minus 1. You guys remember what negative exponents do? Turns into a fraction, so this would become half, which would be 2. I plug in a 1, I get 4 times 2 to the power of 1 minus 1, which is 0. Just gets me 4. S of 2 would be 4 times 2. 2 minus 1, which would just be 2. 2 times 4 is 8. You should see the pattern line 2, 4, 8. Next one would be 16, so this would be yes. It's geometric. R would equal 2. You should notice the next one. 1 to 3, I'd multiply by 3. Then I'd multiply by a fraction, like 2 over 3 to get to that. And then times 3. Then by 2 over 3. Then 3. It's alternating multiplying, but it's not geometric. So it is a pattern. Oops, not geometric, sorry. If you notice the pattern, it's multiplying by 3, and then it's going to multiply by 2 over 3. And it alternates what it's multiplying by. So kind of tricky. I know you guys don't like fractions, but and it kind of alternates times 3 times 2 over 3 times 3 times 2 over 3 times 3 times 2 over 3 times 3. But because it's alternating what it's multiplying by, that is not geometric. And then for D, this would be times negative 1/2. It's like halving, but it's if it alternates kind of from negatives, I know that yes, this is geometric, but oops, my R would be equal to negative 1/2. Let G of n be a geometric sequence where G of 1 is equal to 12 and R is equal to 2. Find the expression for G of n and use the expression. So again, we want to use the second formula up here most of the time. They don't give us G of O. So we're doing G of k, R to the power of n minus k. And we're using G of 1 for G of k. So k is going to equal 1. So G of n is equal to G of 1 is 12. So I'm plugging kind of the 12 in here. Plugging R in. R is 2. N minus 1. Again, the 1 comes from the G. That would be my equation. If they just want you to find the equation for G of N, you can leave it like that. So that would be my equation. They want me to find G of 4. Two to the power of 3, which is 8. 8 times 12 gets me, what? I don't do that in my head. 96? Is that right? I said I want to do it in my head, and I did it in my head. And then again, if you see this kind of curve, you should know it's geometric. Again, you can tell this is kind of like the first one. Again, A1 or A of 0, sorry, is 8. A of 1 looks like it goes to 4. A of 2 goes to 2. A of 3 goes to 3. Or no, not 3, 1. Sorry. I was looking at X. You should see it's halving each time. So my R is going to be 1/2 again. It's halving. Again, they told me A of O this time, so I can actually use this G of N is equal to A of O times R to the power of N. So A of O is 8, and my R is 1/2. So my equation would look like G of N is equal to 8 times 1/2 to the power of N. They want me to find G of 10. So 1/2 to the power of 10. I don't know what that is. Now let me do it in this calculator. It's probably better if I do it in this calculator. 1/2 to the power of 10 gets me that gross number times, what was it? 8. 0.0078125. If I change that to a fraction, comes 1 over 128. I'd probably rather write that. So yeah. So your homework from yesterday still. Looking at this, so again, 1 through 6, you should know at least what geometric is now, so that should kind of help with that. Back here, you should be able to do these. And now you should be able to do everything on the back. Let's actually look at 15 really quick, because 15 is a little different. If they give you 2 G's, we didn't talk about one like 15, so. So one like 15, we didn't do one like this in the notes, where they don't give you R, they could give you 2 G's. So again, we're going to use the same formula. Again, I like to make N the bigger one. I'm going to make N 5, and I'm going to make K 2. And you can almost plug everything in first. So G of 5 is equal to G of 2 times R to the 5 minus 2. Kind of like that. I can kind of plug this stuff in. So again, G of 5, I'm plugging into here. That would be 27. G of 2, I'm plugging into here. That would be, 1. And I can do this up here. Again, I already plugged those in from kind of those numbers. So, but 5 minus 2 gets me 3. I can divide by this number in the front. This is just a 1. So I get 27 is equal R cubed. If I want to get rid of an exponent, how do I get rid of an exponent? I have to take a cube root, so a little 3 root. So that gets rid of the 3, if you remember kind of doing that. And you would get R is equal to, again, 27 is 3 times 3 times 3. So you have 3 3's. So R would be 3. Once you get that, if they want you to find G of N now I can plug in G of 2 and 2 now. So again, I can plug in the 1 My r is 3, and I can leave this as n minus 2 now, and that would be g of n. I think they want you to find g of what, 6? So you can finish that. But 16 should be kind of the same as just stuff with fractions, but same process. So just so you could see one like that on the back. 16 looks kind of like that, just so you know. 17 and 18 are kind of like the last one I did. So sure. I don't know. It was in my other class. Someone got like a 2. Huh? Yeah. My other class, someone like barely put anything. So, but this class, I think it was like a 12 or something. I don't remember. I put it in a different order. But should be somewhere here. Yep. Past it. The FRQ was good, I think. It was the multiple. Was it? I think it was mostly the multiple choice. Yeah. What did I find the score? Yeah. It was mostly the multiple choice. So. Thank you. If you want to try to fix it, you can fix it.
Oh, I didn't do that. I almost forgot. That would have been terrible.
I know.
How did you get like that k equals like 1 over
They told me G is 1. So I said like K is 1.
So would k be 1 here too?
Mm-hmm.
Oh, okay. You need to wait your turn.
Okay, at 1.3.
Is this yours? I think it's your writing. Yeah. You can put your name on it. Yeah. Okay.
Oh, thank you.
This whole table gave me so much like homework.
Thank you. They're literally just different colors. The ones you unlock. You can unlock them all. By just There is someone out there that will pay for that. Oh yeah. I remember watching it.